Electron beam machining.
Learning objectives. At the end of this topic, you will be able to describe about electron beam machining, EBM, explain the basic principle of electron beam machining, EBM, describe the working of electron beam machining, EBM, explain the basic components of electron beam machining, discuss the process parameters of EBM, describe the material removal rate MRR of EBM, explain the efficiency and accuracy of EBM, list out the applications of electron beam machining, list out the advantages and limitations of EBM.
Outcomes. By the end of this topic, you will be able to understand the principle and working of electron beam machining EBM, describe the basic components of electron beam machining, understand the process parameters of EBM, discuss the material removal rate MRR of EBM, understand the efficiency and accuracy of EBM, explain the applications, advantages and limitations of electron beam machining.
Electron beam machining EBM Introduction. Electron beam machining EBM is a thermal process considering the mechanisms of material removal. However, electrical energy is used to generate high-energy electrons in case of electron beam machining, EBM, and high-energy coherent photons. Electron beam machining EBM process is classified into two categories: 1. Thermal type, 2. Non-thermal type. Thermal type EBM. In the thermal type EBM process, the surface of thermoelectronic cathode is heated to such a high temperature that the electrons acquire sufficient speed to escape out to the space around the cathode. The stream of these large number of electrons moves as a small diameter beam of electrons towards the node. As a result, the workpiece is heated by the bombardment of these electrons in a localized area to such a high temperature that it is melted and vaporized at the point of bombardment. Non-thermal EBM. In the non-thermal EBM process, the electron beam is used to cause a chemical reaction. Principle of electron beam machining. Electron beam is generated in an electron beam gun. Electron beam gun provides high-velocity electrons over a very small spot size. Electron beam machining is required to be carried out in vacuum. Otherwise, the electrons would interact with the air molecules, thus they would lose their energy and cutting ability. Thus, the workpiece to be machined is located under the electron beam and is kept under vacuum. The high-energy focused electron beam is made to impinge on the workpiece with a spot size of 10 to 100 μm. The kinetic energy of the high-velocity electrons is converted to heat energy as the electrons strike the work material. Due to high power density, instant melting and vaporization start, and melt vaporization front gradually progresses as shown in the figure 1. Finally, the molten material, if any, at the top of the front is expelled from the cutting zone by the high vapor pressure at the lower part. Unlike an electron beam welding, the gun in EBM is used in pulsed mode. Holes can be drilled in thin sheets using a single pulse. For thicker plates, multiple pulses would be required. Electron beam can also be maneuvered using the electromagnetic deflection coils for drilling holes of any shape. Electron beam machining system. The schematic representation of an electron beam gun, which is the heart of any electron beam machining, is shown in figure 2. The basic functions of any electron beam gun are to generate free electrons at the cathode, accelerate them to a sufficiently high velocity, and to focus them over a small spot size. There are three important elements of EBM system: electron beam gun, vacuum system, power supply. One. Electron beam gun. Electron beam gun is used to produce electron beam of the desired shape and to focus at the predetermined location. EBM gun is operated in the pulsed mode. A superheated cathode, tungsten filament type, generates the electrons cloud. Sometimes, cathode may be used as a solid block indirectly heated by radiation emitted from a filament. Due to force of repulsion from the cathode, electrons move at a very high acceleration towards the anode, which attracts them. The velocity with which electrons pass through the anode is approximately 66% that of light. On light path of electrons, there is a kind of switch bias electrode which generates the pulses. The figure 3 shows the electron beam gun. A magnetic lens is used to shape the electron beam into a converging beam. This beam is passed through a variable aperture to produce the diameter of the focused beam by removing the stray electrons. Magnetic lenses are used to pinpoint the location of the beam, deflect it, and make it a round beam falling on the workpiece. 2. Power supply. The power supply generates a voltage as high as 150 kilowatts to accelerate electrons. The EBM gun of a powerful system is usually operated at about 12 kilowatts and an individual pulse energy as 120 joules per pulse. The power density at the work surface is too high. That is why it is capable to melt and vaporize the workpiece material. Thus, material removal in EBM is basically due to vaporization. 3. Vacuum system and machining chamber. The electron beam generation, its travel in the space, and resulting machining takes place in a vacuum chamber. The vacuum does not allow rapid oxidation of incandescent filament, and there is no loss of energy of electrons as a result of collision with air molecules. The vacuum in the chamber is of the order of 10 inverse 4 to 10 inverse 5 torr. 1 torr equal to 1 millimeter of mercury. Process parameters of EBM. The process parameters which directly affect the machining characteristics in electron beam machining are the accelerating voltage, the beam current, pulse duration, energy per pulse, power per pulse, lens current, spot size, power density. The important parameters in the EBM process are beam current, duration of pulse, lens current, and signals for the deflection of beam. The values of these parameters during EBM are controlled with the help of a computer. This is achieved by appropriately biasing the biased grid located just after the cathode. Switching pulses are given to the bias grid so as to achieve pulse duration of as low as 50 µs to as long as 15 millisecond. Beam current is directly related to the number of electrons emitted by the cathode or available in the beam. Beam current once again can be as low as 200 μA to 1 ampere. Increasing the beam current directly increases the energy per pulse. Similarly, increase in the pulse duration also enhances energy per pulse. High energy pulses, in excess of 100 joules per pulse, can machine larger holes on thicker plates. Material removal rate, MRR, of EBM. The MRR, the material removal rate at which the workpiece material is vaporized, can be calculated from equation 1, where ETA is the cutting efficiency, P is the power, joule per second, and W is the specific energy, joule per centimeter cube. Equation 2, required to vaporize the work material. Specific energy, W, can be calculated as follows. Where Cp is specific heat, Tm is melting temperature, Ti is initial temperature of workpiece, Tb is boiling temperature, HF is latent heat of fusion, HV is the latent heat of vaporization. The cutting efficiency is usually below 20%. Here, Cp is assumed constant, although it varies with temperature. Suffix S and I indicate solid and liquid states respectively. Efficiency and accuracy of EBM. EBM process can be used to machine both electrically conductive as well as non-conductive materials like nickel, copper, aluminum, ceramics, leather, plastics, etc. It has been observed that at the entry side of the electron beam, a small-sized burr, a solidified layer, may be left out. In general, performance, namely MRR, of the EBM process is not significantly influenced by the properties, physical, mechanical, and metallurgical, of the workpiece material. This process can machine small diameter holes 0.1 to 1.4 mm to a large depth, say 10 mm, or in other words, a hole with high aspect ratio, up to 15:1. The geometry of the hole and depth of the hole to be drilled determine the average machining rate, or penetration rate. Further, no mechanical force is applied on the job. Hence, fragile or brittle, thin, and all low-strength workpieces can be easily machined. Off-the-axis holes or inclined holes can also be machined by this process. There is no distortion due to mechanical forces. However, very high temperature gradient would result in residual thermal stresses. Applications of EBM. EBM is more popular in industries like aerospace, insulation, food processing, chemical, clothing, etc. It is very useful in those cases when number of holes, simple as well as complex shaped, required in a workpiece may range from hundreds to thousands, perforations of sheets, etc. This process is also used for drilling thousands of holes, diameter less than 1.00 mm, in very thin plates used for turbine engine combustor domes. Many thousand hole, diameter less than 1.0 mm, in a cobalt alloy fiber spinning head of thickness around 5 mm are drilled by EBM. This drilling is claimed to be 100 times faster than EDM. Holes in the filters and screens used in the food processing industries are also made by this process. The EBM also encompasses the areas like making of fine gas orifices in space nuclear reactors, holes in wire drawing dies, cooling holes in turbine blades, metering holes in injector nozzle of diesel engines, etc. EBM is also being employed for pattern generation for integrated circuit fabrication. In EBM, the beam power, focus, pulse duration, and mechanical motion have been controlled numerically. This would permit more accurate and complex-shaped machining using numerically controlled EBM system, NC-EBM. Advantages of EBM. EBM provides very high drilling rates when small holes with large aspect ratio are to be drilled. Moreover, it can machine almost any material irrespective of the mechanical properties. As it applies no mechanical cutting force, work holding and fixturing cost is very less. Further, for the same reason, fragile and brittle materials can also be processed. The heat affected zone in EBM is rather less due to shorter pulses. EBM can provide holes of any shape by combining beam deflection using electromagnetic coils and the CNC table with high accuracy. Limitations of EBM. The primary limitations are the high capital cost of the equipment and necessary regular maintenance applicable for any equipment using vacuum system. In EBM, there is a significant amount of non-productive pump-down period for attaining desired vacuum. However, this can be reduced to some extent using vacuum load locks. Though heat affected zone is rather less in EBM, but recast layer formation cannot be avoided. The operator also should be a skilled one. The quality of the edges produced is determined by the thermal properties of the workpiece material and the pulse energy. The heat affected zone, HAZ, depends upon pulse duration and the diameter of the hole being drilled. Summary. Let's summarize the topic. Electron beam machining, EBM, is a thermal process considering the mechanisms of material removal. In the thermal type EBM process, the surface of the thermoelectronic cathode is heated to such a high temperature that the electrons acquire sufficient speed to escape out to the space around the cathode. Electron beam gun is used to produce electron beam of the desired shape and to focus at the predetermined location. The velocity with which electrons pass through the anode is approximately 66% that of light. EBM process can be used to machine both electrically conductive as well as non-conductive materials like nickel, copper, aluminum, ceramics, leather, plastics, etc.